Good morning, good afternoon, good evening, everyone. Today I'm going to talk about SPE 209145, or time-lapse monitoring of interwell communication and drainage frac height using geochemical fingerprinting technology with case studies in the Midland Basin. This is written by a few folks from RevoChem and from Henry Resources. This is a case study that Henry Resources wrote in their Midland Basin pad. The objective of this study is to monitor interwell communication and drainage frac height through time-based unique geochemical fingerprint data collected from oils. Results were integrated with independent pressure gauge and well performance data to enable data-driven decisions on well spacing, well stacking, and completion designs with different subsurface configurations. I'll cover the methodology of this presentation. Produced oils of 9 horizontal wells with over 20 months and cutting samples from the vertical section of an adjacent well were collected in the study area located in Midland Basin. The 9 producing wells were from 2 DSUs with 2 different well configurations, one drilled with 2 landing targets and the other with 3. Thousands of chemical compounds are naturally occurring in the produced oils, and oils extracted from the cuttings were profiled and interpreted geochemically. Drainage frac heights and quantitative production allocation by zone were conducted by building geochemistry-based model correlating the produced oils back to their contributing intervals represented by cutting samples and their vertical depths. The probability of interwell fluid communication between each of the well pairs was calculated based on the similarity of the geochemical fingerprints and the produced oils of the corresponding wells. Here is the pad configuration differences between pad X and pad Y. You'll notice pad X has 3 different landing targets with 5 wells. Pad Y has 2 different landing targets with 2 wells. Here's the workflow for the geochemical data acquisition and the geochemical data analytics. And in this paper summary, I'm not going to go too much into detail what the paper covers with similarity index and reservoir quality index, for instance. I'm just going to go over a brief summary and then go straight to the results. For the geochemical data acquisition, you get the baseline rock samples, you do a physical extraction, and then there's a geochemical fingerprint of oil extracted from the rock. And then you do the lab analysis, geochemical fingerprint of produced oils, and then you have a regression model and data analytics. Machine learning models are trained by the RevoChem database, so that's where the data analytics comes in. And that's how you develop the similarity index, their production allocation, and your reservoir characterization indices. And therefore, you end up getting your drainage volume characteristics and your interwell communication. So that's where you get your static reservoir characterization, and then that's how you get your dynamic reservoir monitoring. Here's some of the results of pad X and pad Y. There was a 60% overlap in the drainage frac height between wells targeted in formation B and with formation C. There were 20% overlap drainage in the frac height between wells targeted in formation C and in formation D. With pad Y, there's a 40% overlap in the frac height between wells targeted in formation B and wells targeted in formation D. So obviously we would see a lot more overlap in pad X compared to pad Y. Now here are some of the numerical results of the drainage frac height as well between pad X and pad Y. I'll give you guys a moment to look at some of these values, but you're looking at about 150 to 200 for the drainage frac height for P80, and for the P90 frac height you're looking at from 200 to 400. Now I'll talk about some of the pressure results. Pump intake pressure results were used for interwell communication analysis, especially with pad Y, or pad X, excuse me. And you'll notice the PSI differences when well X3 was turned on and there was an hour top difference between X3 and then X1, X2, X4, and X5. And those are the respective pressure differences that you'll notice. Now here are some of the results between the similarity index vertical and in production. You'll notice that there's low similarity index between X5 and then compared to X3 and X2, meaning that there is a drainage volume that was independent in X5 compared to X3 and X2. X3 and X2 may have shared a similar drainage volume with each other compared to X5. And therefore X5 had the highest oil production compared to the rest of the wells on the pad. You'll notice XY, in which the similarity indices are pretty close, for instance, ranging from 1.4 to 1.6, meaning that there is some overlap in the stacked configuration or the staggered configuration, and the production results are reflected similarly, in which the oil production in well 3, for instance, is pretty much the highest, but everything else is relatively the same. The variations are between 20 to 25% in oil production between Y1 through all the way through Y4. Now, here are the technical well spacing results that are represented in the paper. You'll notice, and this is an age-old, we already know this, in other words, in what's expected in terms of results. Pad X had the most amount of oil production because it obviously has a lot more wells, but Pad Y, for instance, did not have as much oil production. But when you look at average cumulative oil production, you'll notice that Pad X and Pad Y had the largest oil production per well compared to Pad X, and that difference is by 8%. However, with technical well spacing, the one thing that I will mention in looking at this is that it is completely up to the economics on whether if you want to put 4 wells or 5 wells on a pad in this kind of configuration. You really have to run the economic exercise in order to look for future development. So in conclusion, production allocation results show that the 5-well, 3-target scenario generated significantly more overlapped drainage volume vertically and vertical well communication than the 4-well, 2-target scenario. Up to 60% of the drainage frac height in the middle well in the 3-target scenario overlap with the upper wells, and 20% overlap with the lower wells, while the 2-target scenario, the upper and lower wells, only showed 40% overlap vertical drainage heights. Integration of well production data and geochemistry-based similarity index showed a good correlation between similarity index vertical and lateral in well performance, where the lower SI indicates relatively independent drainage air volume, and then there's less competition for drainage from adjacent wells, leading to better performance. On the contrary, wells with higher SI values correlated with lower production rates, indicating significantly overlapped drainage volumes, and well communication could impair well performance. The data also showed significant variation of lateral communication with time, which is strongest in about a month into production and reduced through time. Even with the same spacing and completion design, upper wells showed higher similarity lateral index or more communication than lower wells, indicating geology and completion design parameters such as sand and fluid volume and cluster should be taken into consideration for future planning. Independent pressure data also supported these observations, providing critical evidence for optimizing stacking and spacing and completion designs for future development of wells. That's the end of the presentation, everyone. And this is the overall summary of 209145. For more details of the paper, please check this paper out. Let me know if you have any questions. Let me know if you have any feedback. As usual, please be sure to subscribe, like this video, and comment on the video below on the YouTube platform so I can incorporate your feedback into future videos. Thank you so much for taking the time to watch this video, and I'll see you in the next one.